The hydrohalogenation of an alkene is a fairly straightforward reaction. Are there really 5 ninja levels of hydrohalogenation? Yes, there are. Stay tuned as we'll walk through simple examples all the way up to really complicated. Our first ninja level is the prototypical hydrohalogenation reaction. What we're going to focus on here is Markovnikov's rule in stereochemistry. In the hydrohalogenation reaction, the pi bond acts as the nucleophile at the less substituted side of the alkene, and the mineral acid acts as an electrophile at the acidic proton. The nonpolar pi bond breaks, those electrons bounce through the less substituted side to form the new bond with the hydrogen. This is an example of a bouncing arrow. If you're not familiar with bouncing arrows, I have a video that I'll link down below that introduces you to bouncing arrows. The terminal carbon forms a bond with hydrogen, but that builds up too much electron density around that hydrogen, so we break the HBr bond and we put those electrons onto bromine as a new lone pair. That forms our intermediate, the carbocation and Br-. The terminal carbon formed a new bond with hydrogen. It's not drawn in here. There were 2 implied hydrogens on the carbon to begin with. Now there are 3 implied hydrogens on this carbon in the intermediate. In order to break this bond between carbon 3 and carbon 4, we had to take the electrons away from carbon number 3. That gives carbon number 3 a full positive charge in our carbocation intermediate. I always like to ask myself 3 good questions at every step in a mechanism. First, do I have all of my charges and carbons? There are 4 carbons in my starting material and my intermediate, so I have all of my carbons. We started out net neutral, and we end between the positive and negative. We end net neutral, so I have all of my charges and carbons. Second good question is, can I stabilize this intermediate by resonance? There are no resonance contributors for this intermediate I can draw. Since it's a carbocation, I should look for rearrangement. We have a secondary carbocation, and I can't get any better than that, so no, this carbocation will not rearrange. And third, is this mechanistic step reversible? In the forward direction, the carbon-carbon bond broke. We formed a new bond with hydrogen, kicking out Br- as a leaving group. So the reverse would be Br- taking that hydrogen back, reforming the pi bond. Br- is the conjugate base of a very strong acid. That means it's a very weak base, and unfortunately not a strong enough base to reverse this process, so no, this step is not practically reversible. For the next step in the mechanism, the Br- will be our nucleophile. It has the excess electron density, and carbon 3 will be our electrophile at the full carbocation. The Br- will use one of its lone pairs to attack carbon 3, forming a new carbon-bromine bond, and that will form the product for our reaction. Ask ourselves our good questions again. Charges and carbons. There are 4 carbons in my product. I have all of my carbons. The intermediates were net neutral, and so is my product, so we have all of our charges. Second question is resonance. We don't typically draw resonance for products, so there's no resonance here. And the third question is reversible. Is this step reversible? In the forward direction, Br- formed a bond with carbon 3. So in the reverse direction, the bond would spontaneously break and Br- would leave as a leaving group. Is Br- a competent leaving group? Yes, Br- is a fantastic leaving group. So yes, this step is reversible, and we should denote it with the reversible arrows. And since this is our final product, our bonus question is, did we form any new stereocenter? Yes, we did. Carbon number 3 is a new stereocenter, and we should denote it with a star. To determine the stereochemical outcome of the reaction, we go backwards through the mechanism to the step that formed that stereocenter. When Br- attacked carbon 3 was sp2 hybridized, flat trigonal planar, which means the Br- could approach from either the top or the bottom of that trigonal plane, giving us both the wedged version of the product and the dashed version of the product, where the bromine attacks from either the top or the bottom face of the trigonal plane of the carbocation. This molecule has 1 stereocenter, and it is changed in each molecule, so these are enantiomers. This is a very bog standard, straightforward, prototypical ninja level 1 hydrohalogenation. Our second ninja level introduces the dreaded rearrangement. Rearrangement is so common in this reaction that it only garners a ninja level 2 rating. Pause the video first, see if you can come up with the mechanism and the product for this hydrohalogenation. It's still a hydrohalogenation, so the first step will still be the same. The pi bond will break. The less substituted carbon will keep those electrons to form the new bond with hydrogen, but that builds up too much electron density around that hydrogen, so we break the HCl bond, put those electrons onto chlorine as a new lone pair. That brings us to our first intermediate. Let's go through our good questions. I have all of my charges and carbons. Do you? Resonance. Can this intermediate be stabilized by resonance? No, it cannot. And finally, reversible. Is this step reversible? Cl-, like we saw before, is too weak of a base to reverse this step, so no, this step is not practically reversible. Before we move on to the last step, there's one thing we always have to remember, and that's carbocations can rearrange. Whenever we form a carbocation, almost Pavlovian, we have to look for rearrangement. Carbocation, rearrangement, carbocation, rearrangement. Here we have a secondary carbocation. If the hydrogen from carbon 6 shifts over, that would form a primary carbocation. That's no better. But if the hydrogen from carbon number 4 shifts over, then we can form a tertiary carbocation, and that would be better. So yes, we will do a carbocation rearrangement. We'll break the carbon 4 hydrogen bond. The electrons will stay with hydrogen, and that hydrogen will shift over to form a new bond with carbon number 5. Our next intermediate will be essentially the same, but with the hydrogen shifted over 1 position and a new tertiary carbocation. That hydrogen is now on carbon 5 as an implied hydrogen, and in order to break the carbon 4 hydrogen bond to do the hydride shift, we had to take the electrons away from carbon 4, leaving carbon 4 with a carbocation. Now we're ready for the final step in the mechanism. Chloride halide will act as a nucleophile, and carbon number 4 will act as the electrophile. We'll take the lone pair of electrons on chlorine and use them to form a new bond with carbon number 4. That will form our final product. Ask ourselves our good questions again. I have all of my charges and carbons. Do you? Second question, resonance. Can this intermediate be stabilized by resonance? No, we typically don't draw resonance contributors for products. Third question, reversible. Is this step reversible? In the forward direction, chlorine formed a bond with carbon number 4. So in the reverse direction, this bond would spontaneously break, kicking electrons back onto chlorine. Yes, that step would be reversible. We should draw our reversible arrows for that step. Finally, stereochemistry. Did I form any new stereocenters in my product? Yes, this time I did. Carbon number 4 is a stereocenter. So I should denote it as a stereocenter and at least draw one version of the stereocenter. That stereocenter formed in this last step where chloride attacked the carbocation. This carbocation is sp2 hybridized, flat trigonal planar, so the chlorine can attack from top or bottom. That will form this version, plus it's enantiomer. You're going to see rearrangement on your test somewhere. You've got to start looking out for it now. Ninja level 3 involves the hydrohalogenation of an alkyne. This one is Ninja level 3 because it looks different. The alkyne doesn't look the same as an alkene, but it's still a nonpolar pi bond and it reacts the same as an alkene. Just like Markovnikov's rule says, it's still nucleophilic at the less substituted side and will still attack the electrophilic hydrogen of our mineral acid. The pi bond will break, the electrons will stay with the less substituted carbon to form our new bond with hydrogen. But that builds up too much electron density around hydrogen, so we break the hydrogen-iodine bond, put those electrons onto iodine as a new lone pair. Be careful drawing this next resonance contributor. This internal carbon is still sp hybridized. It only has 2 electron domains. It still needs to be drawn linear. Let's check our good questions. We have 5 carbons in our starting material and 5 carbons in our intermediate. The charge is balanced because we have I- as our leaving group. The next good question is resonance. Can we draw resonance for this intermediate? No, we cannot. The positive charge is on the same carbon as the alkene. It would have to be adjacent to the alkene in order to do resonance. And reversible. Is this step reversible? As we've seen before, I- is not a strong enough base to do the reverse, so no, this step is not practically reversible. Because this carbocation is on an sp hybridized carbon, it will not rearrange. Only carbocations from sp2 hybridized carbons are capable of rearranging. Continuing on in our mechanism, iodide will be our nucleophile with a negative charge, and carbon number 4 will be our electrophile with a positive charge. The lone pair in iodine will form a new bond with carbon number 4. That forms a vinyl iodide at carbon number 4. Charges and carbons. I have all of my charges in carbon. Resonance. No, I can't draw any resonance contributors for this intermediate. And finally, reversible. Is this step reversible? Typically, I- can leave just fine from an intermediate. It is a great leaving group. However, it is attached to an sp2 hybridized carbon number 4. We can't have leaving groups leave from sp2 hybridized carbon. So no, this step is not practically reversible. Now, you might be wondering why I drew this here and not up here as the product. And that's because the number of equivalents of HI was specified and we have 2 equivalents of HI. Had we specified 1 equivalent, this would in fact, yes, be the product. But since we have excess hydroiodic acid, and since this intermediate has its own pi bond, the reaction will continue. We continue to follow Markovnikov's rule. The nonpolar pi bond will break, the electrons will stay with carbon 5 to form the new bond with hydrogen. That builds up too much electron density around hydrogen, so we break the hydrogen-iodine bond and we deposit those electrons locally onto iodine as a new lone pair. That forms a carbocation intermediate. Go through our good questions. We have 5 carbons in both the starting material and the intermediate. The charges are balanced since we have I- as our leaving group. Second good question, resonance. Can this intermediate be stabilized by resonance? Yes, it can. A lone pair of electrons on iodine can collapse down to form a new carbon-iodine double bond, meaning that yes, there is resonance for this intermediate. Last question, reversible. Is this step reversible? Again, as we've seen before, I- is too weak of a base to do the reverse, so no, this step is not practically reversible. Next, iodine is a nucleophile. Carbon 4 is an electrophile. We can take the lone pair on iodide and use it to form a new bond with carbon number 4. And that will form our final product, the geminal diiodide. Quick double check to make sure we still have 5 carbons. We don't typically draw any resonance with any product. Is this step reversible? I- would have to leave on its own. Now it is attached to an sp3 hybridized carbon, so yes, this is a reversible step. And since this is our product, we should look at the stereochemistry. Are there any new stereocenters in this product? There are not any new stereocenters in this product, so we should label this product as achiral. The thing to remember with the hydrohalogenation of an alkyne is we can stop at that vinyl halide if we specify 1 equivalent of our reagent. With 1 equivalent, this is the final product. With 2 equivalents, we continue on to the dihalide. Ninja level 4 introduces us to a tetrasubstituted alkene. The HBr is still electrophilic at the acidic hydrogen, but which side of the alkene is the nucleophilic side? The answer is both. Without any differential substitution, there's no side that's more or less electron rich, and so both sides can equally act as a nucleophile. So sometimes the top carbon will attack the hydrogen, kicking out the bromide as a leaving group, and sometimes the bottom carbon will attack the hydrogen, kicking out bromide as a leaving group. That will actually form 2 possible carbocation intermediates. Now, what is the relationship between these 2 molecules? The red version is just a pancake flip of the orange version. These are identical molecules. In fact, if you notice the plane of symmetry in the starting material, that would have predicted that these carbocations would have been identical. Now, had the starting material not been symmetric, we would have gotten 2 different carbocations and 2 completely different answers, And I would submit that's not a very well set up hydrohalogenation. We don't really try to set up reactions that form two completely different products. That guarantees you're wasting at least 50% of your material, and that's not a very green chemistry reaction. But with a symmetric alkene, these two carbocations are identical. In both of these intermediates, I have all of my charges and my carbons. Neither of these carbocations can be stabilized by resonance, nor will either of these carbocations rearrange. They're already tertiary carbocations, and we can't do any better than that. And this step will still not be reversible. Br- is still too weak of a base to reverse back to the alkene. When the Br- attacks in the next step, which carbocation will it attack? It doesn't matter. They're the same molecule drawn twice. So we'll have the Br- attack carbon number 2, and that will form our product with the new carbon-bromine bond. Charges and carbons check out. There's no resonance for this molecule, and yes, this step is reversible. Br- can be a leaving group. But what about the stereochemistry of this product? Are there any new stereocenters in this molecule? Yes, there are. 2 of them, actually. Carbon 2 and carbon 7 are both stereocenters. So let's go backwards in the mechanism to see where we form those stereocenters. The stereocenter at carbon number 2 formed in this last step where bromide attacked this carbocation, which is flat trigonal planar sp2 hybridized. That means the bromide could attack from the top or the bottom, and we can get a mixture of stereocenters at that position. About half of the product will have bromine on the top, and about half will have bromine on the bottom. But carbon 7 is also a stereocenter. Where did that one form? The stereocenter at carbon number 7 formed here in this first step when carbon number 7 attacked the hydrogen. This carbon number 7 is also sp2 hybridized, flat trigonal planar, so when that pi bond goes to attack hydrogen, this HBr could either be on top of the alkene or on the bottom of alkene, again giving us a mixture of stereocenters at carbon number 7. And that's very interesting because we had a mixture of stereocenters for carbon number 2. So that means for the version where bromine was on the bottom, about half the time, the hydrogen on carbon number 7 will be on the wedge, and the other half of the time, that hydrogen on carbon number 7 will be on a dash. Same thing for when bromine is on a wedge. Half the time, this hydrogen on carbon number 7 will be on a wedge, and half of the time, that hydrogen will be on a dash. So it's not really good enough to say there's a stereocenter, so plus enantiomer, racemic mixture, plus minus. That won't always be true. If we look at these products that are made, it looks like these are enantiomers, and these are a pair of enantiomers, but the relationship between these two molecules is diastereomers. These are also diastereomers, diastereomers, and diastereomers. So one stereochemical label doesn't really fit this product. It's certainly not achiral. It would be inappropriate to say a mixture of enantiomers because some of them are enantiomers, but some of them are diastereomers. So the most accurate stereochemical description is to draw one version of the product and write mixture of 4 stereoisomers. When we form 2 stereocenters and they're both variable, we get 4 possible total stereoisomers in this product. Watch out for that if your alkene is tetrasubstituted or you find other reactions that can form 2 stereocenters. Our 5th ninja level introduces a sneaky example of Markovnikov's rule. As set up, this looks like a regular hydrohalogenation reaction. We have HCl, which is an electrophile, and we have the alkene, which can be a nucleophile. We'll ignore the aromatic ring. If you've not learned about aromatic rings are exceptionally stable and don't involve in reactions at this point. The question is, which side of the alkene will be the nucleophilic side? With no difference in the degree of substitution of either side of the alkene, you might think that both sides react indiscriminately to form 2 different products. So let's take a look at that. We could have the carbon on the left attack the hydrogen, or the carbon on the right attack the hydrogen. When the carbon on the left attacks, we have to take the electrons away from the carbon on the right. That gives us a carbocation on the carbon on the right. And when the carbon on the right attacks, we take the electrons away from the carbon on the left, giving us a carbocation on the left. Now, both of these carbocations are secondary, and Markovnikov's rule says that we should form the most stable carbocation intermediate possible. One of these carbocations is more stable than the other. Do you see it? It's true, both of them are secondary, but the carbocation next to the benzene ring can be stabilized by resonance with the benzene ring. The carbocation further away cannot. Because this is a resonance stabilized carbocation, it is more stable, and Markovnikov's rule says will form the most stable carbocation intermediate possible. This carbocation will effectively not form. Since this intermediate can be stabilized by resonance, we should show all additional resonance contributors. So when we draw the arrows for this mechanism, we should only show the arrows that form this most stable Markovnikov carbocation. Having checked charges and carbons, resonance, and reversibility, we're ready for our next step. The lone pair on Cl- will form a bond with the carbocation carbon to form our final product. We get the product with the new carbon-chlorine bond, which is a stereocenter. It attacks the carbocation, which is sp2 hybridized, top and bottom. We get both versions of the stereocenter and a racemic mixture. Great work, ninjas. Now you're ready for any hydrohalogenation your instructor can throw at you. Thanks for watching. If you like what you saw today, maybe let your instructor know about these videos, or your friends at other schools. Check out some of these other videos and playlists, see what you like. As always, don't forget to like and subscribe.